Math 3a section 2.8, the derivative as a function. So if we start with saying we use this symbol f prime of x to represent the derivative of the function. For the derivative of f of x, again this is read as f prime of x. So f prime of x equals, what is the definition of f prime of x? You know, from pre-calc we taught you what we call quotient, difference quotient, fx plus h minus fx over h. If we take the limit of this as h goes to 0, that gives me what f prime is. That's what f prime is. So to apply it, find f prime of x for the function y equals f of x equals x cubed plus x minus 1. Let's start with this one. So this is the definition of the derivative, the one I just showed you, this one. I'm putting a frame for that. Okay, so f prime of x is equal to the limit as h goes to 0 of f of x plus h, means x plus h cubed plus x plus h. I'm substituting x plus h for every x, minus 1. Then there's a minus there, another minus, the function itself, which is x cubed plus x minus 1, all over h. Now that's where the algebra kicks in. So we always write the limit as h goes to 0 down until we simplify everything. So if you remember from the Journey to Calculus packet, we give you a formula for a plus b cubed, which says you cube the first one plus 3x squared h plus 3xh squared plus h cubed. And then x plus h stays the same, minus 1 the same. Multiply the negative inside, so minus x cubed minus x plus 1 all over h. These cancel out. 1 minus 1 cancel, negative x and x cancel. So you get the limit as h goes to 0. On the top you can factor an h out. You get 3x squared plus 3xh plus h squared plus 1 all over h. These cancel. If you pass the limit inside, you get 3x squared plus 0 plus 0 plus 1. So the answer is 3x squared plus 1. That's the derivative for that function. That's f prime of x. Any questions about this? After you finish this, we're gonna do it, find the derivative for this function, this second function. So we're gonna find or apply the same definition to this function right here. So f prime of x is given by the limit as h goes to 0 of f of x plus h. So what I'm gonna do, every x will be replaced with x plus h over x plus h plus 1 minus the function itself all over h. Okay, this equals the limit as h goes to 0. What are we gonna do here? This is called complex fraction. From the Journey of Calculus, packet of calculus here, you notice that we had shown you how to simplify complex fractions like this. So what do? We look at all the denominators, this, this, and this. And what's the LCD? The LCD is x plus 1 times x plus h plus 1. X plus 1 times x plus h plus 1. You multiply the top of each fraction by the LCD, which is x plus 1 times x plus h plus 1. Now, What do we do next? This will clean up this and this. That will leave negative x plus h times x plus 1. Negative times negative positive x. This will cancel this. X plus h plus 1. The denominator never expand. Leave it as is. Now, try to finish this up. Try to finish this up. So now, we need to multiply the top ones. You get negative x squared, negative x h, negative h, plus x squared plus xh plus x, all over h times x plus 1 times x plus h plus 1. These cancel, these cancel, these cancel. Oh my god, everything cancels. The h cancels. So that leaves only negative 1 on the top. X plus 1 times x plus h plus 1 as h goes to 0. So this will go to 0 now. That leaves negative 1 over x plus 1 times x plus 1, which is x plus 1 square. X plus 1 square. Next, we have a third function here. Each function looks totally different than the previous one. We need to find the derivative of this using the definition of derivative, as we did earlier. Okay, so the first step would be f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. If you guys got that, that's good. Now we need to find the LCD to all of them. This, and this. What's the LCD? The LCD is 2 times the square root of x plus h times square root of x. 2 times square root of x times square root of x plus h, and 2 times square root of x times square root of x plus h. That's the LCD. Let's see what that gives us. Limit as h goes to 0. Here these cancel out. The 2 cancel. You get root x minus. Cancels. Square root of x plus h. 2h square root of x times square root of x plus h. Notice if you pass the limit as h goes to 0, you will get 0 over 0. So what do we have to do in this case? So here we need to rationalize the numerator. Multiply top and bottom by the square root of x plus square root of x plus h. Square root of x plus the square root of x plus h. So what do we get here? Limit as h goes to 0. The top one, we take the first one, you square it, minus the second one and you square it. Keep this the same. And this square root of x plus the square root of x plus h, like that. Then what we need to do is, on the top we get x minus h. These cancel. 2h square root of x, x plus h, square root of x plus the square root of x plus h. H cancels, so you get negative 1 over 2 square root of x, square root of x, square root of x plus square root of x. Negative 1 over 2x times 2 square root of x. That gives me negative 1 over 4x root x. Now, you have to show all this work on the homework or on the exams. So we now introduce a definition of differentiable functions. Definition. A function, namely f, a function f, is said to be differentiable. So you're gonna get used to this. Differentiable at, let's say, point x equals a, if the derivative at that point exists. Okay. Now we say if, or let's say it is differentiable over the interval a b, or negative infinity to infinity, or a to infinity, or negative infinity to a, if it is differentiable at every point in that interval. So we say a function is differentiable over any of these intervals if it's differentiable at every point at that interval. Means the derivative at every single point in that domain or that interval exists. Of course, it's hard to probably comprehend the whole concept unless if you see examples. As an example in this, we may ask, let f of x be the absolute value of x. Is f differentiable? Is this differentiable? Well, let's see. The first thing I'm going to do is I can rewrite by definition the absolute value of x as positive x if x is positive, negative x if x negative. So we're going to start with the first function. Start with f of x equals x. And what are we going to do to check if the derivative exists? Let's find the derivative of this function first, using the definition of the derivative. This equals limit as h goes to 0. Fx plus h is x plus h minus x over h. These cancel, you got 1. Yay. How about the other one, the negative x? Also, f prime of x equals limit of fx plus h minus f of x over h as h goes to 0. So replace x with x plus h minus negative x over h. Negative x minus h plus x over h. These cancels, the h cancels, that'll leave a negative 1. Since one of them has a derivative 1, was one negative 1, they're not the same. So we say the function of x equals the absolute value of x is not differentiable. It's not differentiable. And I'll show you specifically what happened with this graphically, what happens. So now we move on. We move on to a different one. Sorry, not different one. Let me explain more about this. When you graph y equals absolute value of x, if you remember the graph, it goes like a V shape like this. This part is the positive x, y equal positive. This is the negative x. So what happens, the function is not differentiable at 0 at that point. Not differentiable here. At x equals 0. If you remember from before, when we want to find the equation of the tangent line, we define the derivative at a point to be the slope of the tangent line. The slope of the tangent line. So what happened here, we can write as a note, at the origin, at that point, f has no tangent line. No tangent line. So it's not differentiable at that point. So in general, this motivates us to tell you the specific cases where the function is not differentiable. Okay. One of them when we have what we call them corner points, if it's like this or like this, at these points you can draw no tangents, right? No tangents at this. No tangent. So it's not differentiable. Another specific case, when you have a graph like this, so you can't have a vertical tangent line like this because it has an undefined slope, vertical line. The slope is undefined. So not differentiable. Call this point here A. Not differentiable at A. This A, the point A, is called cusp. It's called cusp. Are there more cases? Well, yes, there are. There is. Let me see if I can draw it. I hate this, drawing this, but something like that. So when you have, at that point, the function is not differentiable. Also where we have vertical tangent line. So we can write a function fails to be differentiable. At the corner points or cusps, sharp points at vertical tangents. And at the point of discontinuity. So if you have a function that goes this way and then it continues this is not differentiable at this point. Not continuous, not differentiable. Now, we introduce a theorem that would help if a function is differentiable, then it is continuous, but not the other way around. So we say the converse is not true. Means if the function is continuous doesn't mean it's differentiable. So let's say y equals absolute value of x as a counterexample, and also y equals the cubic root of x. Those functions are continuous. They are continuous functions, but not differentiable. Notation. So notations, we told you f prime of x means the first derivative, y prime. It's called first derivative of f of x. So y prime, different people write differently. Some people write dy dx. That's called Leibniz notation. We had a mathematician with the name Leibniz. He used to use this notation, dy dx. That means you're finding the derivative of y with respect to the variable x. I've seen people write this one, dy dx, like that. I've seen people d sub x, like derivative per x, or derivative of f of x per x, or d of f of x. For higher derivatives, y prime is the first derivative. If we find the derivative of the derivative, that's called the second derivative. Y double prime is the derivative of the derivative. And the way we write that down, you're finding the derivative of the first derivative with respect to x, which can be written as d square y dx square. That's the second derivative. We have y triple prime. It's the derivative of the second derivative. So that's the third derivative. Y to the fourth is the fourth derivative. We can go to the nth derivative. So now let's say we're given f(x) equals x cubed plus x minus 1. Find y prime first. Actually, we did find y prime earlier. We found that f prime or y prime was 3x squared plus 1. We need to find the second derivative now. Watch carefully how we find the second derivative, or y double prime. Is the limit as h goes to 0 of what? Remember, in f of x we wrote, in f prime we wrote f of x plus h minus f of x over h. But in y double prime is f prime of x plus h minus f of f prime of x over h. Try it this way now. So we move on with this. So y double prime equals the limit as h goes to 0. Replace x with x plus h square plus 1 minus the function itself all over h. So this equals the limit as h goes to 0 of 3x squared plus 6xh plus 3h squared plus 1 minus 3x squared minus 1 all over h. These cancel. So you get the limit as h goes to 0. Take an h out, you get 6x plus 3h all over h. These cancel. So that gives me 6x. Yeah, if you want, we can find the next one. Can you find the third derivative? Try the third derivative. So y triple prime. So y to the third power or derivative is the limit as h goes to 0 of f double prime of x plus h minus f double prime of x all over h. So limit as h goes to 0, 6 times x plus h minus 6x over h. So that gives me the limit as h goes to 0, 6x plus 6h minus 6x all over h. These cancel. That gives me 6. That's the third derivative. Can we find the next derivative? Y to the fourth. Y to the fourth is the limit as h goes to 0. F triple prime of x plus h minus f triple prime of x all over h. Limit as h goes to 0. F triple prime we just found at 6. So if you replace x plus h for x, there's no x, so you just keep it 6. And this one is also 6 over h. So you get 0 over h, which is 0. And anything beyond that is going to always stay 0. Always is going to stay 0. We're going to look at some applications. Okay, some applications. We first recall and introduce this. S of t represents the position function at time t. That's what S of t is going to be. V of t is going to be the velocity function at time t. A of t is the acceleration function at time t. So V of t is S prime of t. That's how we calculate V of t, which is ds dt. A of t, it's V prime of t, dv dt. And we can also call it second derivative of s. So velocity is the derivative of the position. Acceleration is the derivative of the velocity, or double derivative of the position function. Let s of t equals 2t squared minus 5t. Find the acceleration. Try this one, very important to try first. So first, to find the acceleration, we need to find the velocity, which is s prime of t. Limit as h goes to 0, s of t plus h minus s of t all over h equals limit as h goes to 0, s of t plus h. So that's 2 times t plus h square minus 5t plus h minus the whole function 2t squared minus 5t over h. Limit as h goes to 0, 2t squared plus 4th plus 2h squared minus 5t minus 5h minus 2t squared plus 5t. A lot of algebra work involved. Equals limit as h goes to 0. 5t minus 5 cancel. 2t squared minus cancel. Take an h out. You get 4t plus 2h minus 5 all over h. These cancel. So the answer becomes 4t minus 5. So this is only v of t. We need to find the acceleration now, which is, so say now a of t equals the derivative of v. So it's the limit as h goes to 0 of v of t plus h minus v of t that we just got all over h. Limit as h goes to 0. V of t plus h is 4 times t plus h minus 5 minus the whole function 4t minus 5 over h. Limit as h goes to 0. 4t plus 4h minus 5 minus 4t plus 5 over h. These cancel, h cancel. That gives me 4. Now I want to show you how f and f prime are related graphically based on the graph. So I have constructed some guidelines or summarized some guidelines. If you have in the function, say I have a function like this point or that point, that's where there's a horizontal tangent. At these points, these 2 points A and B, if you want to translate it onto the graph or to sketch the graph of f prime, those 2 points, they become on the x-axis. If the function is going up, means increasing, then the graph of the derivative will fall above the x-axis. If it's decreasing, it falls below the x-axis. Okay, if you guys are done, let's say we have a graph of this function f. We need to sketch the graph of its derivative. Without knowing, of course, the equations. So what do we do here? First thing I do, I look at these points here, call it point A and point B. Those points, they're going to become on the x-axis. So it's going to be some point on the x-axis. And this point is going to be dropped up on the x-axis as well, like this. It's going to be here. If the function is increasing, then the derivative falls above the x-axis. So probably something like this. Decreasing, this is decreasing here, it's going down, so it's going to be below the x-axis. And then increasing from B on, so it's going to be above the x-axis. So this is above the x-axis, here below the x-axis, because it's decreasing. Because the blue graph decreases, the graph of the green one should be below the x-axis. If the graph of the blue is increasing, the graph of the green one is above the x-axis. Above the x-axis. Any questions about this?
So, Professor, when we do the homework of